that I have. And there's a reason I have these other minerals out. And this mineral, Wulfenite, you can see the chemical formula for said mineral on the screen here, as well as in this here. Well, let's turn it the other way so you can actually read it, yeah. There we go. So that is a little piece of Wulfenite. It's actually pretty low in the hardness. It's only got a 3.5 to 4 in hardness, and it's actually pretty brittle as well. So these little crystals, and you'll see, I'm going to show you on Mindat their shape up close. You'll see why this is actually such a fragile specimen. Those individual crystals actually break off very, very, very easily. So PB is lead, MO is molybdenum, and then O is oxygen. So it's a lead molybdate. Sorry, it's a lead molybdate. In the Strunz classification system, they actually classify it as a sulfate. Yes, a sulfate. And the reason why is because the tungstates, the molybdates, the vanidates are all very rare relative to the bigger group sulfates. And the group of sulfates have the exact same building block structurally and shape. So this is why I wanted to use this picture here. So really quickly, I'm going to go into a basic building block of this mineral. So if we look at the overarching group of sulfates here, which is really cool, you'll see that this little chemistry building block there, you see those little tiny red dots with the smaller dots in the middle? That's actually the basic tetrahedron. Now, this is obviously a two-dimensional picture, so you can't see it in 3 dimensions. But the SiO2, the quartz tetrahedra, well, it's technically the tetrahedra basic building block of the silicates is SiO4. But that's kind of another topic. So that tetrahedra is the basic building block for the silicates. For the sulfates, it's 4 oxygen surrounding a sulfur. It's the same exact thing for the tungstates, the chromates, and the molybdates. Instead of sulfur being in the middle, you've got molybdenum and also chromium, or tungsten, or was it molybdenum, tungsten, chromium? I think those are the other 3 that they actually mentioned. Yeah. So they form the same exact structure as the sulfates do, which is why in the Strunz classification system, you'll see on Mindat that it says it's actually a sulfate. But technically, chemically, it's actually a molybdate because there's no sulfur in there. It's just molybdenum, lead, and oxygen. And that's only the basic building block of this mineral. Because if you see the chemical formula here, there's also lead. So it gets more complex than that. But the basic building block is just a tetrahedra, which is why they lump it in with the sulfates. I would not like this mineral, no. In fact, I would actually wash your hands after handling Wulfenite because there's lead in it. Galena is also lead-bearing. That actually brings me to my next point. This mineral is actually a secondary mineral. It's actually not a primary. It's secondary because it forms due to oxidation of zones that have a lot of lead-bearing minerals like Galena. So it's a very, very unique mineral in that way. It's actually pretty common, however, for the molybdates. It's, I believe, the second most common molybdenum-bearing mineral after molybdenite, which is a mineral, by the way. I'm sure that, no, this Wulfenite was named after the man who discovered it in Austria. I think Wulfen something was his last name, but it was in the late 1700s that they discovered this mineral. This mineral is actually pretty common for a molybdate. It's all over the place. There are really fantastic mines for this mineral in Arizona, Mexico, and some other localities that I personally forgot because, well, my favorite samples are from Arizona and Mexico. Even the sample I have is from Arizona. It's from a mine there. Let's go back to the mineral scene. I don't remember what was his name, actually. I'll tell you right now. It's somewhere in here. Wulfen. F.X. Wulfen, 1728 to 1805, an Austro-Hungarian mineralogist. Oh, and it was named in 1845. But, okay, so it was named after his death. Sorry, I was in the wrong century. Oops! Which is the most dangerous toxic to handle? Oh, gosh. There's a good list of them. It just depends. Well, I mean, there's the three that's always taught in every level 300 mineralogy course: realgar, orpiment, and cinnabar. Because they're all sulfides that have either mercury or arsenic in them. But there are also radioactive minerals like uraninite. Chalcanthite is slightly toxic if you have sensitive skin and allow it to oxidize and powder and then inhale that powder. That's also a potential problem. Wulfenite, well, isn't great because it has lead in it, so I would recommend washing your hands after you handle it. So just be aware of what is in the chemical formula of the minerals you're handling, is what I would say, to be honest, if you're concerned about it, Doxy. I did a toxic mineral thing the other day on just some of the toxic minerals that I have. But I don't have a bunch of them. I have cinnabar, I have orpiment, I have wulfenite. I mean, I have a lot of lead-bearing stuff, actually. Supposedly malachite and azurite can be somewhat toxic. I've never had any issues with it. Yeah, and of course, Doxy. But yeah, like I said, I would always look up, and that's a great, go to mindat.org. Here's a great way to figure that out. Go to Mindat, and any mineral, literally almost any mineral, they're going to have information on it. And eventually, if you scroll down on the mineral in question, it'll give you an option to take you to the health information, if there is any. There is some health information for chalcanthite. And I think for cinnabar, I haven't looked at all of the minerals, but there's definitely health issues or health information. And it'll also tell you the chemical formula. Even if you go to a site like eRocks and decide to buy minerals, they'll tell you in the information if it requires special handling. Usually they should, especially the radioactive ones. Breathing in any powdered minerals would be really bad. It can, for example, breathing in volcanic ash can lead to silicosis, where the ash actually turns into cement in your lungs and your stomach. I have a small chunk of galena, which actually I should get out for this. It's just a very tiny one, and it's metallic. Little guy. Because the galena is actually a very, very good thing to talk about, because this is the mineral. Galena is one of the minerals that are one of the primary minerals that forms in the areas that later become oxidized and produce minerals like wulfenite. So wulfenite's actually a secondary mineral. It forms in areas where there was galena and then oxidation happened. And you'll notice at the end of the chemical formula of wulfenite, there's an O, which stands for oxygen, and there's not one for galena. It's a sulfide. So the sulfur gets replaced essentially. And lead is in galena, so molybdenum has to be in the area as well for this to form. So galena is a lead sulfide. So all you need to do is essentially oxidize it and add some molybdenum, which seems like, oh yeah, that's all you need to do. But chemical processes, this actually happens naturally. These happen. And it's really, really interesting and cool. And we can study this via lab models, and we can notice it and take notes of it happening in our Earth. It's pretty neat. Hydrothermal deposits can alter things and add ions through hot water into various areas as well, adding things like, well, molybdenum. It's a cute little galena, I know. Talk a little bit more about this. Cleavage. You remember that cleavage is a geologic or mineralogic property that has to do with the type of bonds, the chemical bonds that bind all of these different elements that you see in that chemical formula together. So you can have metallic bonds, van der Waals, you can have ionic, covalent, all hydrogen bonds, all sorts of different things, right? And then these things, right, these different minerals in the three-dimensional space that they exist on a specific direction and plane, and there is a classification system for all of the different planes, and it's really obnoxious, and I'm not going to go into it. But on a very specific plane, it can break preferentially. That's called a cleavage plane, and that's what that is. Yeah, and a mineral can still fracture, but if it fractures not preferentially, then it's just called a fracture. And yeah, we can describe fractures via various descriptors as well, like hackly and conchoidal, etc., etc. But the cleavage planes are the nicest, as they can provide us a really good piece of evidence for specific minerals sometimes. Sometimes that cleavage plane is that extra edge, what we need to identify that mineral. And sometimes there are angles between multiple cleavage planes. That's that last piece of evidence we need. Differentiating different groups of minerals, like the pyroxenes and the amphiboles. Those are two really big groups of minerals that are so similar that one of the best ways in hand sample we can use to identify them is their angles between their cleavage planes. No joke. Pyroxenes have an angle between two cleavage planes at about 90 degrees. Amphiboles have a 120 and 60 degree cleavage plane break. So you'll see that difference in angle very, very clearly, because those minerals typically can be pretty big. They do weather more quickly than their quartz and feldspar counterparts, however. But if you find them, it's one of the really interesting ways to identify them. Yeah, no, how it breaks apart, how it cleaves is literally one of the things that we use as an identification method. Hardness is something else we use as an ID method, right? So the Mohs hardness scale goes from 1 to 10. The Mohs hardness scale is what we teach in most of the geology classes. Vickers hardness is the quantifiable way in which we can determine a mineral's hardness, but we don't really use that as much. Not in practicality. It's great to have that number so we can compare them, but the Mohs hardness scale is typically what we use. And Wulfenite sits at a 3.5 to 4, so it's not going to be one for jewelry typically. It's pretty soft. It's crystal forms that it makes. It typically makes these really thin tabular faces that are, I don't know how conducive they would be to jewelry, honestly. You'd almost want to just facet one just as is. Habit is basically, it's tabular, right? Habit is how it grows, how it forms, the shape that it makes. So back to, we talked about cleavage, which is on the atomic scale, the preferential ability for a mineral to break along a single plane, or in some cases up to 4 planes. Fluorite, one of the more common minerals, actually has 4 planes of cleavage. This only has 1 distinct plane. It has another that's kind of poor, but you'll see the plane at which I'm talking about. The streak is white, so if you were to take it along a streak plate, like this one here, this little guy, it's kind of like a piece of a chalkboard. You would see a literal white streak on there, as if you had taken a white colored pencil to it or something. Metallic minerals, a lot of the metallic minerals are oftentimes the ones with the most color. But I've also noticed a lot of copper-bearing minerals also have a really colorful streak too. Not all the time, but a lot of the time. Okay, color, orange, yellow, reddish, can be kind of brownish sometimes. But a variety of orange is generally the most common samples I've seen of Wulfenite. Just bright orange, like what you see in this sample. It's typically, its luster is adamantine to resinous. I forgot to look up its index of refraction, but I really like knowing that. Adamantine is essentially probably close to a 2 as an index of refraction. The more shiny something is, the closer to an index of refraction that's up towards the number of metallic, not close to metallic. Metallic is on a different end, but so this would be considered metallic, right? You can see that. This is, however, adamantine, or in this case, maybe vitreous. All those individual crystals, they look kind of like, well, they're just shiny, right? You'd kind of describe them as shiny. I look at this and I'd say, oh, that's vitreous. That's very vitreous. Possibly subadamantine in this case. The crystals are so small, it's really hard to see. But you can, again, back to this being a secondary mineral. This is a secondary mineral from this guy here. This is a lead. This has lead and sulfur in it. That's the only 2 chemical components in this. is lead and sulfur. So you've got lead in this guy too, but you also have oxygen because that sulfur was removed and replaced by oxygen, thereby being oxidized. And there was some molybdenum in the system as well, yielding the molybdate wulfenite. So again, secondary mineral and oxidation zones. Secondary mineral and oxidation zones is where you'll find wulfenite. It's got I think it's got a specific gravity of around, I want to say 5 or 6. Let's look at it. That's not it. That's not what I wanted. Wulfenite, I can't remember the specific gravity is. Yeah, it's 6.5 to 7.5. It's very dense. Now, I can't really tell with this specimen because there's matrix on the back that isn't wulfenite. But if I had just the wulfenite crystals, I could definitely tell that it's got a weight difference. The Galena is one of the minerals. You can absolutely feel a weight difference. It's extremely dense. It's just lead and sulfur. I want to see the specific gravity of Galena. It's the mineral from which it forms typically. Oh, its density is 7.58. Maybe they didn't calculate the specific gravity. Specific gravity is calculated slightly differently than density is, but it's a very dense mineral. It's just very cubic. Yay, Galena, so fancy. But one of the things you could see that these are very tabular in shape typically. They're very thin individual crystals oftentimes that are like this. They're just really thin little tables. A bunch of them. So it's a very brittle mineral. So you can imagine if you've got just a bunch of these like kind of sticking out, they're going to break really easily. So you got to be delicate with this sample. Because it's quite nice, but this will break right off. It would probably break right off. Mine is kind of more in between both this and this. So this is a really good range of colors, to be honest. It's a tetragonal crystal system. We talked about that in the beginning. So in this case, the molybdenum is surrounded, the lead is surrounded by, no, not the lead, I'm sorry, just the molybdenum. The molybdenum is surrounded by the 4 oxygen in a tetrahedron pattern. So that's the basic building block of this, which is why it's in the crystal system of the tetragonal system. Oh, the diaphanate. So that has to do with how see-through is this thing. It's honestly all of the amounts. So it can literally be translucent, transparent, or opaque. Can be all of them, from opaque to transparent. Its refractive index, I forgot to look up. It is brittle. We talked about that. It's tetragonal. It's a molybdate, which is a subgroup of the sulfates, and we talked about that. It's because of their structure. We talked about its occurrence as being in oxidized areas where lead and molybdenum-bearing hydrothermal sulfide deposits occur. Its uses are typically to mine for ore or molybdenum, and it's oftentimes used as a collector's item and not jewelry because it's just too soft to use for jewelry unless you can find a very, very talented. It's also a member of the scheelite group, which is this guy here. No. Big. And it, I think, is just describing their crystal shape. Group of tetragonal molybdates and tungstates with the general formula given above, where A denotes a relatively large divalent cation, either calcium or lead, and X is a molybdenum or tungsten. So that's why it's A instead of A and X instead of actual periodic symbols. Scheelite. This particular sample of mine is from the Raleigh mine in Arizona. I actually haven't looked that up. Let's see what else they produce. Oh, there's some ruins there? Whoa. A former copper, lead, silver, gold, molybdenum, vanadite, barite, fluorspar mine. Oh, wow. It's located in Arizona. Discovered in 1900. Oh, they stopped using it in 1923. Oh, huh. It's in the Painted Rock Districts, too, in the Maricopa County from Arizona. So that's the specific location of my mineral, which is really interesting and neat. I like to know where it's from. All right. Now, finally, why is vanadite and cerussite there? Well, I found out it's vanadite right here. And cerussite, they actually sometimes form in the same areas where oxidation of galena is happening. So I thought I'd bring them up. Additionally, they, cerussite will be found in those areas. Vanadite is also in the group of sulfates because it shares that same basic building block. And I really like it, but it's quite brittle. You can see where little pieces have fallen off, but it's actually quite a brittle sample. This is it's actually really dense as well and pretty heavy for its size. Even little tiny crystals. So that's vanadinite. I like it. It's kind of a blood red brown. I really, really like that. Another is Celestite. This is another sulfate with the same basic building block. It's a strontium sulfate, however, and it's also extremely dense. It's very heavy. This guy I actually got from a shop in Colorado. I don't have the original locality for it, but I really like that gray blue, kind of dark, almost storm cloud color. And I also love this crystal shape here. It's quite unique and interesting. So that's why I pulled those guys out. And cerussite is a lead-bearing carbonate, so this is the one that'll actually form sometimes due to oxidation of galena in areas that there are the chemical components necessary to form this. So this is a carbonate, and this is a molybdate. This is a sulfide. Pretty cool stuff, guys, right? So this cerussite sample, I've got a little bit of video on my Instagram. And this specimen is actually considered adamantine. Its index of refraction, or the amount of light that actually reflects off of the crystal planes, it's pretty high. It's higher than a lot of other minerals. It's very, very pretty. It's a very unique shape, too. I find it quite interesting and unique. It's stinky, though. I don't know why it's so stinky. And I hate it. Oh, no, I think I lost the paper that goes on it. No, it's right here. I need to get a sticky tape and put that on there better. So finally, let's look at these crystals of Wulfenite under the microscope camera. All right. Ooh. Oh my goodness. I'm trying to find a nice tabular crystal to show the side of. It's kind of just, oh, there's a nice, there's a little guy. There's a little guy. There's a little guy. He's kind of broken. You can see where it's fractured and not broken on the cleavage plane. Ha ha ha! Some of these crystals, by the way, Wulfenite crystals, can get up to like 10 centimeters in size pretty often. So unlike dioptase, this is, the crystals can get quite large. Oh my god, that's so gemmy. It's really pretty. Let's look at it even zoomed in more. The gray in the background is just the matrix on which it formed. Now this is zoomed in even further on individual crystals. Trying to. There we go. Almost looks like glass up close. There must be a fracture plane right there. Kind of resinous, honestly. Not quite as shiny there. Might be covered in some dust. He's a camera shy guy. A little camera shy guy. Come back, little camera shy guy. There's another fracture surface. See if I can get a decent one in here. That one looks nice. Hey, come back here. You come back here. That's a nice tabular surface. It's hard to get the, because they grow at angles and kind of up toward the camera, it's hard to see the sides of them. Let's see if I can get one on the side. So you can kind of see the sides now. I'm holding it at a different angle. You can see all those different little tabular surfaces that grew on that. See that? Very, very cool. I need to wash my hands now from playing with this. No, my fingers! It just shows how tiny these crystals actually are. Very, very pretty. I love it. Oh no! What? No. Oh my goodness! My Tektite!